Hello and welcome. Let's start doing some dynamic modeling using first principles models. Some very simple systems. So here is a heated surge vessel, and what you have is cold feed going into the tank, which is heated, and what is exiting the tank is a hot stream. So T is greater than T naught, and you're putting in Q kilojoules per minute or Q megajoules per minute of heat into the tank, to the liquid in the tank. What we want to do is we want to get the response, how Ca responds as Ca naught changes, how the temperature T responds as T naught changes, and F naught is supposed to be constant. So F naught is constant. F naught is constant. So this is the problem, and as usual we'll make some assumptions and then develop a model using material and energy balances. So this is a very simple system. Let's develop a model. So what are my assumptions? We'll assume that the tank is well mixed. There is no heat loss. Properties are constant. They don't vary with temperature. Volume is constant in the sense that it's just flow through a pipe kind of thing. And F naught is constant, and Q is given. So for a given Q, we want a model that predicts the change in T as T naught changes, change in Ca as Ca naught changes. So now let's first look at the change in Ca as Ca naught changes problem. So the material balance would be, volume is constant, so V times dCa by dt, this would be equal to what's flowing in minus what's flowing out, and what's flowing in and what's flowing out are the same, and let that be called F times what's flowing in is Ca naught and what's flowing out is Ca. So if you take all the Ca terms on one side, what you will get is and this is equal to Fca naught. Make the coefficient of Ca 1, and what you get is then dividing by F. So this is the governing dynamic material balance equation, and you can see that the units of this guy, V is meter cube, flow rate is meter cube per minute or meter cube per hour, as the case may be. So meter cube per hour, let us say. So you can see that this has got units of time. So we call this a time constant, and we'll say that this is equal to tau. And then what we get as our governing material balance equation is tau dCa by dt plus Ca is equal to Ca naught. This is our governing material balance equation. Now, in order to solve this, we can use the integrating factor approach, and what we are doing is, see, Ca naught initially, Ca naught at the initial steady state, which I'll denote by this guy, and Ca at the initial steady state, I'll denote by this guy. And you can see that if you're initially at rest, the exit concentration must be the same as the inlet concentration. So what you have is Ca is equal to, yeah. Now to solve this, you can use the integrating factor approach. So let me just, maybe it's easier to do it this way. To solve that differential equation, we need to use the integrating factor approach, and my governing equation is tau dCA by dt plus Ca is equal to Ca naught, and we will say that Ca naught changes as a step at time t equal to 0. So initial value of Ca naught is Ca naught bar, and it increases by delta Ca naught. Yeah. So let's use the integrating factor approach to integrate this equation. We have to put it in standard form for using integrating factor. And the integrating factor here is e to the power integral of this guy dt exponential of integral of 1 by tau dt, which is equal to e to the power t by tau. So multiplying both sides by e to the power t by tau, what you get is e to the power t by tau times dCA by dt plus 1 by tau e to the power t by tau Ca is equal to 1 by tau e to the power t by tau times Ca naught. We'll put in Ca naught a bit later. And the left hand side then simplifies to, that's the idea behind using an integrating factor. And you can see that if I differentiate this guy, I'll recover this guy. And this is equal to 1 by tau e to the power t by tau Ca naught. Ca naught we are going to integrate from t equal to time t equal to 0 onwards, and at time t equal to 0 is when we have given the step. So if you do this, then we get a very neat, then Ca naught is a constant, and we get a very neat separation of variables. And so what you get is integral of differential of e to the power t by tau Ca is equal to integral of, and Ca naught is a constant, Ca naught by tau is a constant, integral of e to the power t by tau dt. And what this gives is with a constant of integration, or you can put limits of integration. So I'll just put limits. So what you get is integral of a derivative is the function itself. So by the way, this entire thing is derivative. So what we will get is e to the power t by tau Ca from 0 to t should be equal to, and if you integrate this, this will be e to the power t by tau times tau, because you'll have to divide by 1 by tau. So So the tau and the tau will cancel, so what we'll get is Ca naught e to the power t by tau between 0 and t. And if you further put in the limits and put, you see, Ca at time t equal to 0 is equal to Ca, that's at time t equal to 0, and this is equal to at time t equal to 0 whatever is the value of Ca naught. Initially the system is at rest. So if you put all this, what you will get is e to the power t by tau times concentration of A at time t hang on. Okay, this is fine. So that's at time t minus e to the power t by tau at time t equal to 0 is 1 Ca tilde or Ca over bar, the initial steady state value. This must be equal to Ca naught at time t is Ca naught plus delta Ca naught. That's what it is at time t. And we'll just do the e to the power t by tau minus 1. And you can see and of course the whole thing is multiplied, and one can see that if you divide by e to the power by t by tau, then this cancels, and here what you'll have is divide by 1 by e to the power t by tau, and then you'll say that okay, C of A at time t is equal to Ca naught at the initial steady state plus delta Ca naught into 1 minus e to the power minus t by tau. And the point to be noted is that so Ca naught into 1 remains. So okay, so I've skipped a few steps, but you'll find that this is what you get. There is a cancellation that occurs, and that cancellation is occurring. So if you divide, so this guy will also be divided by e to the power t by tau. And so delta Ca naught times e to the power minus t by tau. So these two terms will cancel out. This is minus Ca bar by e to the power t by tau, and when you multiply this guy with this guy, you'll get the same term, so they will cancel out, and then what you're left with is this. So the solution to this very simple problem with the initial conditions as shown here is, so the solution is hang on, maybe I'll just remove everything. So if you have tau dCa by dt plus Ca is equal to Ca naught as your governing differential equation, its solution for a unit step change in Ca naught is Ca is equal to Ca naught initial plus change in Ca naught. This is the solution that we get for change in concentration of the vessel exit stream if the vessel inlet stream concentration changes as a step. If we look at the energy balance in order to get the variation in T with T naught, if you look at the energy balance, what we will have is rate of accumulation rho V Cp, where Cp is mass heat capacity, and we are assuming these guys are constant. Properties don't vary with temperature, or and that's a reasonable assumption. This is the accumulation of energy. This must be equal to enthalpy in minus enthalpy out. Enthalpy in is rho F Cp T, and out is T naught, and out is T, so T naught minus T, and you're putting in heat at this rate. So this is the energy balance, and if you divide by rho F Cp, what you get is rho Ncp. So what you get again is V by F dt by dt, rate of change of temperature, plus T is equal to T naught plus 1 by F rho F Cp times Q. And again, if you replace this with the time constant T, what you get is, and replace this with a gain called K, and this is the gain K between T and Q. So the effect of Q on T, effect on T of Q. Yeah, so we will call this KTQ. So what you get is tau this is the governing differential equation that relates T to T naught and Q. If you looked at previously what we did for material balance, if you know how Ca varies in response to a change in Ca naught, what we had was we had a step like this, and the output Ca varied as, we just derived this equation, we had Ca varying as Ca naught, or C, which is the same as Ca, so you don't need to put the naught there, plus 1 minus e to the power minus t by tau delta Ca naught. So what this gives is actually, if you look at it in terms of deviation variables, Ca deviation, deviation from the initial steady value, where the initial steady value is this, is actually, so it's much easier to look in terms of deviation from the initial position of rest, from the initial steady state. Equations become much simpler. So this is what we got, and this is exactly the same. I don't need to derive it again and again. So what we should get here is T response in response to a change in T naught would be this guy times delta T naught, and T response in response to a change in Q would be, because it's multiplied by K, so linear system, so the response will be multiplied by K. So what you will get is K TQ into 1 minus e to the power minus T by tau times delta Q. It is convenient to put, delta Q will be kilojoules per hour, so you'd rather look at percentage change, because this is a change in percentage. If you can go to 800 megajoules per minute, then and you are giving in 400 megajoules per minute, then you are at 50%. So it is convenient to put things in terms of percentages, and one way to do that is to scale Q with respect to its initial steady value. So let's say the initial steady value is Q bar. Then we'll say that okay, T is equal to K, and I'll remove the TQ there, times 1 minus e to the power minus T by tau times delta Q on a percent basis, where delta Q percent is defined as whatever is the current Q divided by whatever is the change in Q divided by whatever was my steady value of Q at the initial position of rest. And so it can be derived as, divided by Q times Q, and therefore this is Q percent, and therefore what you get is K is equal to KTQ times Q bar. Yeah, it's more convenient to work in terms of percentages, but in either case the point is express the differential equation in terms of difference variables, and when you work in terms of difference variables or deviation variables, where the deviation is from the initial steady position, then you get very neat responses of this kind and of this kind. Yeah, so to summarize, that was my material balance, this was my differential equation, where tau is equal to V by F is a time constant. Notice that this tau is dependent on the operating conditions. If I increase the flow rate, if the flow rate increases, then tau decreases. Yeah, this is very typical of processes. Higher flow, lower residence times, and the time constant of the process then decreases. But the point is, the governing equation is an ordinary differential equation, and the parameters or the constant coefficients in that differential equation, or the coefficients of those differential equation, are dependent on the operating conditions. Okay, so this is the differential equation, and we got the solution. Initial condition is this, and this is what we got derived using integrating factor approach. Time constant as shown for the variation of t to a change in t naught. We saw this, initial condition was this, and we had variation in t to a variation in t naught, and variation in t to a variation in q. And what I also showed was that this k can be made k, and this guy can be made delta q percent, where k is equal to k tq times initial steady value of q. Yeah, so that's that. This is how you solve these equations. Now let's look at the response. Let's look at the responses. By the way, again here, depends on operating conditions. The gain also depends on operating conditions. So that's a major point. For a first order ordinary differential equation, you got a gain. See, with respect to Ca naught, the gain is, delta Ca naught, the gain is 1. With respect to T naught, the gain is 1. With respect to delta Q, the gain is KTQ. Okay. The point is, the gain is also dependent on, in general, the operating conditions. And you can see here, if flow rate increases, time constant goes down, gain of T on Q also goes down. Yeah, that's very typical of chemical processes. You start flowing more stuff through it, time constants go down, gains also go down. Yeah. So these ordinary differential equation coefficients depend on operating conditions where you are operating at. So I've just taken a very crude problem, a very simple problem. Flow rate in is 1 meter cube per minute. Volume of the tank is 10 meter cube, so tau is equal to V by F, comes out to be 10 minutes. Yeah, Cp is very typical of organic mixtures. Density is again very typical of organic mixtures. And the temperature rises from 20 degrees Celsius to 60 degrees Celsius. So Q steady state must be rho Cp delta flow rho Cpf times delta T, and delta T is, well, delta T is delta T. So if you plug in those numbers, 800 times Cp is 2.55 kilojoules per kg times flow rate is 1 meter cube per minute times 40, what you will get is 81600 kilojoules per minute, which is the same as 81.6 megajoules per minute. So that's the amount of heat that is being put into the system. And for this system, if I look at the responses, if Ca naught going in is 10 kilomoles per meter cube, let us say Ca naught goes from 10 to 15. That's the step change that we give, from 10 to 15 kilomoles per meter cube. That's Ca naught. Yeah, so if we do this kind of a change, so Ca naught goes from 10 to 15, and you can see the exit concentration immediately starts responding, but it takes its own time. Ultimately it will reach 15, whatever is the inlet concentration, but it takes time to reach there. And you can also see that in one time constant, the response changes by, I don't know, so the response is 1 minus e to the power minus t by tau. Yeah. So if t goes to 10 times delta Ca naught, yeah, if t goes to 10, then I'll get 1 minus e to the power 1. So in one time constant, if you calculate this, this will turn out to be 0.632. So that means 63.2% of the response gets completed in one time constant. That's typical of a first order ordinary differential equation. I am sure you would have seen this probably in a physics course somewhere. Yeah. You can do these calculations, and maybe I should have done it, but I have not done it. But just from memory, if you go two time constants, the response would be about 85% complete. If you go three time constants, response would be about 95% complete, and so on and so forth. Okay. So that's a first order typical response. Similarly, if you change temperature from 60 to 61 degrees Celsius, inlet temperature changes from 60 to 61 degrees Celsius, the outlet temperature goes from 60 to 61. Oh, I'm so sorry. Inlet temperature is this guy, huh? And temperature is this guy. Okay. So inlet temperature goes from 20 to 21, increases by 1 degree Celsius. So outlet temperature also increases by 1 degree Celsius. It goes from 60 to 61. Okay. So if the increase in inlet temperature is 1 degree Celsius, increase in outlet temperature is also 1 degree Celsius. That makes sense. And again, 63.2% of the response, about 2/3 of the response completes in one time constant. So this is the total distance that the response has to travel. About 2/3 gets completed in one time constant. If you look at the response of the temperature to a change in Q, to a 1% change. So if the valve is at 50%, 1% of 50% would be 0.5%. So the heater duty valve position goes from 50% to 50.5%, which is a 1% change. And in response to this, you see that temperature goes from 60 to about 60.4 degrees Celsius. So the gain K is actually 0.4. Yeah. And again, the time constant, total change is 0.4. You travel about 2/3 of the total change. You go 2/3 of the way in one time constant. One time constant. Yeah. So that's that. Now let's put in a proportional controller. So what I do now is, okay, so I've got my proportional temperature controller, which compares the tank temperature with the set point and then adjusts the heater duty Q, adjusts Q using the proportional control law. The action of this controller is reverse, in the sense that if temperature is increasing, decrease Q. And what we have is, of course, what we have is the governing energy balance equation is this, which we saw previously. And now we are saying that Q is equal to Kc times proportional deviation away from set point, T set point minus T, and that's reverse action, plus a bias term which would be the initial at rest value of Q. So that's Q, and of course there is a K here, and put a percent there, so maybe I'll also put a percent here and a percent here. So if we substitute this guy here, Q percent coming from the control law, then what we get is proportional control law K Kc times T set point minus T plus K times Q steady state, initial steady state. Notice that if I look at this equation at the initial steady state, if I look at this equation at the initial steady state, rate of change is going to be 0. So at the initial steady state, what we have is so instead of kq percent, I can substitute instead of kq%, I can substitute t minus t naught. So let me do that. So we'll substitute t minus t naught steady state, and let me take this t to the left hand side. So then what I'll get is t times tau times, where t tilde is actually equal to the deviation variable t minus t steady state, plus t tilde, because t minus t over bar is t tilde, is equal to t naught minus t naught bar is going to be deviation from t naught, plus kkc, and t set point is going to be set point is going to be, initially it's going to be t bar, and then I'm going to increase that set point probably by a delta t, yeah, minus t. The other two terms I've taken care of, and so this turns out to be minus t. See, this also turns out to be deviation variable. So what I get from this is that my governing equation is tau. It's much more convenient to work in terms of deviation variables, because then the initial conditions are 0, is equal to t naught plus kc into delta t sp minus t tilde. And now take that t tilde term to the right, to the left hand side, and what we get is tau over 1 plus kkc dt tilde by dt plus t tilde is equal to 1 over 1 plus kkc t naught tilde plus kkc over 1 plus kkc into delta t set point. So this is again a first order differential equation, and now you have a equivalent time constant of the control system, which depends both on the operating condition and on the controller tuning. What is the value of kc that you're using? The gain of t naught is dependent on the controller tuning parameter. The gain with respect to delta t sp is also dependent on the controller tuning that is being used. Okay, and again you can use the integrating factor approach, but by inspection you can tell that if you have a change in t naught, if t naught changes by delta t naught, then is going to be, we'll call this tau prime, t, the deviation in t is going to be 1 over 1 plus kkc into 1 minus e to the power minus t by tau times t by tau prime times delta t naught. Similarly, we will have, if delta t set point is changed by delta t sp, then we'll have the deviation in t is going to be kkc divided by 1 plus kkc into 1 minus e to the power minus t by tau prime. Note that tau prime depends both on operating conditions and the controller tuning times delta t sp. This is the other chap. Maybe I should highlight this. Well, highlighting is not very good, so delete कर दो इसको. Okay. This is the basic result. Key point to be noted is that, see, this chap, when there was no control, this gain was 1. That means if delta t increased by 1, t would increase by 1. If inlet temperature T naught increased by 1, temperature would increase by 1. With control, I have this, if Kc is large, you are dividing by a number that is greater than 1. It could be much greater than 1. Delta T naught increases by 1, T increases by 1 over 1 plus kkc, which is much smaller than 1. So now you see temperature is not being allowed to deviate too far away. The deviation is much less. It's not 0, but it's much less than 1:1. Similarly, over here, if delta t set point is increased by 1 and if Kc is large, this guy is almost 1. Because this guy is almost 1, so what that means is temperature reaches very close to the set point. Yeah. And just to make these points, I'll show you some dynamic plots. But before we do that, it's good to summarize. So yeah, so governing equation, controller equation, using deviation variables, what you get is this guy, and I derived this. You can also derive this. How do you derive it? Just substitute whatever you got for t into this equation, and then you will get this guy. Yeah, I'm not going to do that. We'll leave that as an exercise for you. So that's the regulator set response. That's the servo response. And again, one has to realize that this depends on both operating conditions and controller gain. And these gains with respect to set point and temperature depend on the controller gain. If you look at the responses, if delta T naught was 1 degree Celsius, if you had no control, temperature would have increased like this and gone to 61. Yeah, we saw this previously. But now we've got control, and because we've got control, if I'm using a gain of, if kkc is 1, that means kc is, because k is 0.4, so kc is 1 by 0.4, 2.5. So a kc of 2.5, this is the response that you get. A larger kc, how much would this be? 2.5 divided by 0.4, 25 divided by 4. How much is that, mate? 6 point something, whatever. And kkc of 5. So these were the results that I got. You see, as you increase the gain, kc is increasing in this direction. As you increase the gain, you get a faster response. You reach steady state earlier. Here you are reaching steady state after so long. Here you are reaching steady state much earlier. So it takes longer. As you increase kc, the response becomes faster, and your deviation away from the desired value of 60 degrees Celsius becomes smaller. No control, the deviation was 1 degree Celsius. When you're using kkc is equal to 5, the deviation is only, I don't know how much. You can calculate kkc divided by 1 over 1 plus kkc. That's what it is. So 1 over 1 plus 5, so 1 by 6, that's what it is, 1 by 6 degrees Celsius. And you also see that the change in the Q, which is this subplot, you get more aggressive change and you require larger change, and because of this larger change the deviation from set point is smaller. The deviation away from 60 degrees Celsius, the desired value, is smaller. If you look at the servo response where the set point is being changed, again when KKC is small you do go towards the set point but you have a large offset. Crank up the gain and then you get a smaller offset. Crank up the gain further and you get a much smaller offset. And you also notice that as KC is being increased, that means the controller is being made more aggressive. You make larger changes in U. You can see that here, larger changes in U, and the response completes quicker. So here, for example, it takes it takes two open loop time constants for the response to complete. The black curve, the response is completing, I think, in one time constant or less than one time constant, one open loop time constant. And that has to do with the fact that your tau prime, the closed loop time constant, was tau over 1 plus KKC. So as Kc increases, tau prime decreases, and so your response is faster. Now, this is typical of control system. More aggressive control, you get to set point quicker, response completes faster. Of course, as you will see later on, you can also get oscillations and instability, but for now some major observations that you need to take note of. So observations are: smooth response, response speed increases with Kc, aggression in Q increases with Kc, and with proportional controller you do get an offset from the set point, and the magnitude of this offset decreases as Kc is increased. Now, as an exercise, what I'd like for you to do is consider a tank with perfect level control. So F naught is equal to F all the time. A P controller manipulates the outflow. So there is a level controller that manipulates the, and just assume that F is proportional to valve position. So there is a level controller that manipulates the outflow, and assume a linear valve. So F, the actual outflow, is proportional to controller output. Let's call this U. Okay. So you got this level controller. A P controller is manipulating the outflow. Obtain expressions for the variation in level and outflow to a change in set point of the level controller or a change in F naught. So this would be the servo response, this would be the regulator response. So obtain the servo response where the level set point changes, and obtain the regulator response where the F naught changes as a step. This would be an exercise that is very similar to what we have done in class in this lecture. So do this as an exercise. So in summary, dynamics of some very simple systems are described by a first order ODE. The first order ordinary differential equation is parameterized by its gain and time constant. These parameters generally depend on operating conditions, usually decrease with throughput, flow through the system. Throughput is the flow through the system. The response is usually described by a decaying exponential e to the power minus at. By the way, if you look at e to the power minus at and if you plot it with respect to time, it will start from 1 and then it will go to 0. That is its nature. And if a is increased, it will go to 0 faster. Yeah. We've also looked at proportional control of a first order system, and with proportional controller the dynamics is described by a first order ODE. The ODE parameters depend on both the operating conditions and the controller gain. Get a smooth dynamic response. You get an offset from the set point. Higher controller gain causes a faster response time and a lower offset. This is what we have seen. With this we come to the end of this lecture. I thank you for your attention. Hope to see you next time again. Thank you and goodbye. Adios, amigos.